Welcome back. Continuing on the derivative, let's take a look this time at a velocity versus time graph. Maybe I'll start it up here this time. It's going like that. Now the slope of a velocity versus time graph, I can write that like this, or I could write that like this, the derivative of v with respect to time, that is the slope. That's going to equal the acceleration. Now I'm going to make up an equation that describes this curve. And so let's just say that this equation is described by the following graph. It's 4 meters per second cubed times t squared. Notice I'm putting in units this time. I didn't put in units the first time because I was trying to make it a little more simple, but let's see how units work out with this. So the speed is equal to, the velocity is equal to 4 meters per second cubed times t squared plus, let's go with 2 meters per second. That's the equation. So like if I put in at 0 seconds here, this is going to be 0. So it turns out that this must be 2 meters per second right here. Okay, now if I want to find the acceleration then, well, the acceleration, the slope, is changing every point along the way. And so to find the acceleration, I'm just going to take the derivative of v with respect to t. Well, you see we have two terms this time, and I'm just going to take each term separately. In fact, this term, 2 meters per second, that's really like 2 meters per second times t to the 0th power, because anything to the 0th power is going to be is equal to 1. So that's what that's like. Okay, so to get this derivative then, I'm going to take this coefficient and multiply it by the coefficient, this exponent, and multiply it by the coefficient. And so that's going to be 8. And I'm going to leave the units alone. It's just meters per second cubed. And that's going to go to t to the first power this time. And then plus, I put 0 times 2 is 0. And so that's going to be 0. In fact, the derivative of a constant is always going to be 0. That makes sense because, let's take a look. If I have a graph of v versus t of just a constant v, what is its acceleration? 0. What is its derivative? 0. What is the slope? 0. Okay, so let's see how the units work out on this then. At t equals 0, the acceleration apparently is equal to, put in 0 for this, it's 0 meters per second squared. At t equals 2 seconds, let's say, the acceleration is, if I put in 2 seconds for that, that's going to be 16. Now the seconds will cancel with the seconds cubed, and that's going to leave me with meters per second squared. So the units will work out. Notice that the derivative then, it doesn't just give you the slope. It's giving you a function that describes how the slope, what's happening in the slope at every point along the way. So it's a little bit more powerful than just giving you the slope at a particular place. It actually gives you the recipe, the function for finding the slope at any point on the graph. So that's pretty neat. Okay, now I need to tell you a little bit about the antiderivative. So let's take a look at the antiderivative. Imagine that you have an acceleration of an object. You have the function for it. Let's say that the acceleration for an object, making these up again, just as I go, the acceleration of the object is equal to, let's go with 4 meters per second to the 5th power times t to the 3rd power. That is the function for the acceleration of some object. Hey, do the units work out if I put in 1 second here? Will all this stuff turn out to give me meters per second squared? You bet. All right, well, here's the thing. What if I wanted to know what the velocity was of this object? Well, I know that whatever the velocity is, when I take its derivative, I have to get this. And so what I'm going to do is I'm going to think backwards now. I'm going to actually think backwards as I try and find the velocity. I'm going to take the antiderivative. And so that's just thinking backwards. So let's see, I'm going to have a t there. And this is going to be lowered. When I take the derivative to get the acceleration, it's going to get lowered by 1. So I'm going to put this as a 4. I would like to end up with 4 meters per second to the 5th power. And so I'm going to put that there. But underneath it, I'm going to put whatever's coming down. I'm going to put that here so it negates whatever's coming down. So this stays the same. Let me take the derivative of that and see if that works. Let's see. I would bring this over, and that would give me just 4 meters per second squared. And then I would take 1 away from this, and that would be t cubed. So that's the velocity. So that could be the velocity of the object. Could this also be the velocity of the object? If I put on, say, maybe 4 meters per second. What if that were there? If I took its derivative, would I get this? Let me see. This is a t to the 0th. Let me take the derivative of this and see if that gives me that. So if I take the derivative of v with respect to t, that's going to give me, sure enough, it's going to give me 4 meters per second to the 5th, t to the 3rd, plus this is going to give me 0 because the derivative of a constant is 0. So I could have any term here. I don't know what this term is here. So the way that this works is when you don't know what the term is, you do the following. You just say the velocity is going to be, this can be simplified to 1 meter per second to the 5th, t to the 4th, plus there could be a constant. You say that there could be a constant if you do that. Well, that just means then that if there's a constant, we need more information on the problem. So they would have to tell us, say, for instance, the problem would have to say, hey, the acceleration is this. It's that equation. But at t equals 0, v equals 2 meters per second. If they tell us this as well, now I can figure out what c is, because at t equals 0, come on down here. If I put in a 0 for t, this whole term goes to 0. So the only way that v can be equal to 2 meters per second is for c to be 2 meters per second. So this is the new equation. So to get the value of c, you need to know some other conditions about it, about the problem. Let me just conclude then that when you take the antiderivative, you're thinking in reverse about the derivative. All right, see you next time.